We regularly train models on paired data, like a video and audio track. The default approach encodes these signals into a single fixed embedding space, but modalities are inherently asymmetric. A high-resolution image contains dense spatial details, while a short text caption offers sparse, abstracted meaning. They differ in coverage, resolution, and the specific types of noise they carry. When an architecture forces these heterogeneous inputs into a uniform representation, it creates an inescapable bottleneck. The model must make a mathematical compromise. We map this compromise with a multimodal latent factor model, decomposing data into 3 variables. The shared factor captures semantic overlap in both text and image. 2 modality unique factors hold context found in only one channel, like a visually specific car color. A monolithic embedding forces a choice. The model must either align the shared factors perfectly, often at the cost of discarding unique cues, or try to retain everything and absorb massive amounts of noise. Because this architectural choice rigidly caps the upper bounds of model accuracy, we have to look closely at the math behind our most common training objectives. Contrastive learning, popularized by models like CLIP, is the dominant method for aligning multimodal data. These models operate on a specific mathematical objective, maximizing the mutual information between paired modalities. The problem emerges in the factorization. Mutual information is driven entirely by the shared factor. Mathematically, the modality unique factors make zero contribution to the cross-modal mutual information equation. Under the data processing inequality, any information lost during encoding cannot be recovered by downstream predictors. The contrastive objective systematically filters out unique signals. If a downstream task relies on a high-resolution visual detail completely absent from the text caption, a contrastive model will fail. The necessary data was discarded before the task even began. Researchers recognize this blind spot. To fix it, many turn to InfoMax-style approaches. An InfoMax model takes the opposite path. Its objective is absolute fidelity, actively retaining both the shared and the modality unique information. But total retention creates a structural problem. By saving everything, the embedding absorbs dense layers of task-irrelevant variables. In information theory, a variable is task-irrelevant if it is conditionally independent of the goal. InfoMax captures these useless variables alongside crucial signals. When it comes time to execute a task, downstream predictors waste compute trying to filter through loaded, noisy representation. The monolithic architecture leaves us with 2 bad options. Contrastive models lose the needle, while InfoMax models preserve the needle by burying it in an ever-expanding haystack. To build a better model, we first need to define the mathematical requirements for an optimal multimodal representation. This diagram illustrates the first requirement: task sufficiency. The model's representation must function as a sufficient statistic for the target task, retaining every signal relevant to the output. The second requirement balances it out: the principle of information minimality. This brings us to S3, a framework designed to replace monolithic embeddings through specialization, selection, and sparsification. S3 achieves this by repurposing the mixture of experts architecture. Rather than using experts to scale up parameter counts, it uses them to semantically decompose the data. Stage 1 is specialization. The framework breaks multimodal inputs down into distinct, interpretable concept-level experts. Instead of collapsing everything into a single point, these experts populate a distributed semantic space, organizing the data by individual concepts. Stage 2 is selection. S3 introduces a routing mechanism to navigate this newly structured latent space. For every input sample, this router evaluates the specific demands of the downstream task and dynamically activates only the relevant experts. If a concept does not serve the immediate goal, the router explicitly bypasses it. This selective activation directly addresses cross-modal asymmetry by ignoring the noise unique to each channel. By composing a custom representation out of specific semantic components, S3 satisfies task sufficiency while completely avoiding the InfoMax noise trap. The final stage, sparsification, refines the model entirely at inference time. No additional training is required. The model reviews the routing paths and intentionally prunes the network, forcing low-contribution experts to zero. When tested across multi-bench datasets, this intentional dropping of information produces a consistent, counterintuitive result. Model accuracy actually goes up. This chart plots model sparsity on the x-axis against accuracy on the y-axis. It reveals a distinct reverse U-shaped trend. As the model grows sparser, its performance scales up, right until it crosses a critical threshold. That peak on the curve is the mathematical point of information minimality. Task-irrelevant noise is maximally suppressed, while the necessary, unique signals are preserved. Sparsifying these routing paths is the physical mechanism that finally solves the problem of retaining unique data without drowning the model in noise. Forcing asymmetric data into a uniform representation is a structural dead end. Aligning modalities require them to be grounded in semantically coherent structures, rather than relying on brute force signal compression. Specializing distinct concepts, selecting for the task, and sparsifying the noise creates a dynamic architecture that adapts to the data rather than fighting it. For engineers handling complex datasets, semantic decomposition provides a mechanism for interpreting model behavior and optimizing computational load. Scaling multimodal performance requires architectures that can isolate relevant signals while remaining mathematically minimal. Selection, not just collection, is the key to information minimal representation.